Okay, now we are starting section 2, 9.2. And this we are discussing theoretical and experimental probability. Theoretical and experimental probability. Okay, so let's talk about what each one is. Theoretical is what should happen in an experiment. For an example, if toss a coin (100 times), you would expect 50% heads. Okay, that's what you would expect because it's a 50-50 shot of landing on heads or tails. Okay. Experimental is what actually happens after an experiment. And we all know we flip coins, for some reason it always lands on one side versus the other. Okay, it's what actually happens after an experiment of many trials. Okay, all right. I went ahead and filled in the information for this for the essence of time for the video. Okay, we're playing the game of rock, paper, scissors. We've all played that. Okay, so for the theoretical probability, that's what would happen when it takes place. Okay, so if you're playing in rock, you both land on rock, then it's a tie. If it's player A lands on rock or fists a rock, then and paper covers rock, so player B wins. Rock beats the scissors, so A wins. And you can go ahead and think about the situation for all of those. Okay, so we're going to talk about what's the theoretical probability for this situation and answer these questions right here. Okay, so what's the probability of player A winning? How many times is there an A in this grid? Remember that probability is what you want over the total. Okay, well, how many total games are there here that have played? 9. So the denominator is going to be 9, and we want the probability for A to win. So this is the notation to tell you what's probability of A. Okay, so this is red. Probability of A winning is what you're thinking when you see this notation. So how many times is there an A? 3 out of 9, which simplifies to 1/3, which is the same as 0.3 repeating, which is 33.3% with the bar over it. These are all of your final answers if you're writing it all 3 forms. Okay, but right now we're just going to continue with fractions for comparison purposes right now, but you will be asked to show all forms. Okay, so now we have, what is the probability of player B winning? Well, how many B's are there? 3 out of 9, which simplifies to 1/3. What is the probability of a tie? It's 3 out of 9, which is 1/3, which is what should be kind of expected. You've got 3 options that can happen, and it's 1/3 of each. That's the theoretical. That's what you think should happen. Now let's see what actually happens. Okay, so we had a pair of people, that partner A and partner B, they did 25 trials of playing the game. Okay, so that means that my total is 25. Okay, so the total is 25 because we did 25 trials. All right, so what percent, so we're asking for percents now. When we ask for probability, you're usually wanting your answer in fraction form, okay? Percent, all right, so trials for partner A. So again, it's written the same way, it's probability for A, but the thing is, we're wanting the percent of an experiment. So how many A's won? 9 out of 25, okay? That's the fraction, but I want it as a percent. So the easiest thing is to change this to a decimal, which is going to be handy data calculator enough time, or you can see I can multiply times 4, but it's your choice, whichever is easiest. 9 divided by 25, it's 0.36, which gives me 36%. This is the answer that I write because it wants percent. It is asking me to find the percent. Okay, what percent of the trials did partner B win? Okay, so B is, oh, that's 7 out of 25. So I have to do 7 divided by 25, which gives me 0.28, which is 28%. And now what percent of the trials resulted in a tie? Well, this one happens to be the same. It's a 9, so I don't have to really do any calculations because I've already done that work. I can just recopy it since it happens to be the same fraction. So we have 0.36. Make sure I'm recording. And that's 36%. Now, this is where, so far, it's just like simple probability. Where we get into it, it throws a little bit more for us to do is where we have to compare the theoretical and the experimental, which is coming now. Okay, do the theoretical results match the experimental results? Are they the same? If I look at the probability for A for the theoretical and A for the experiment, what do I notice? Well, it's 33% for all of these because it's all 1/3. It's much easier to compare when it's as a percent or a decimal. Okay, much easier to compare as a decimal or percent. That's why you want to write it in all the different forms. Okay, so do the theoretical results match the experimental results? No. A's win. A's wins were higher B's wins were lower. You have to describe what you notice. That's the big thing. You've got to describe what you notice. And the ties were higher than expected. A lot of times these answers are going to be, as long as they're a correct description, you may not have the exact same words, but they do need to have an accurate description of the data. It may not be the exact same as what I might write, but it's got to be an accurate representation of the data. You couldn't say the B's are higher than the A's when it's actually the A's are higher than the B's. And you would have to say the probability of, or the A's wins. You have to be descriptive and detailed. Okay, so next. How could the experiment results get closer to the theoretical results? Well, what could be done? You could do more trials and the results will get closer to the theoretical. The bigger your experiment, the closer the results will become to the actual theoretical results. So the larger the experiment, the closer the theoretical and experimental will be. All right, next page. this down. So now we're going to look at if they give us an example. Okay, the table below shows the results of rolling a standard die. Remember that a standard die, okay, a standard die has 6 sides, okay, numbers 1 through 6. 50 times, that's my total. Okay, what is the theoretical probability of rolling a 4? So we have probability of 4. That's just what's the chance of rolling a 4. How many 4s are on a numbered dice? 1. So this probability is 1 out of 6. Okay. So remember I said it's easier to compare, and if I read on, compare this to the theoretical. I'm comparing, so I'm going to go ahead and write this as the decimal and the percent as I'm going. 1 divided by 6. So that's going to give me 0.16 repeating, which is 16.6 repeating percent. And these are my answers here. All right, so next, now it's what is the experimental probability for rolling a 4? So that's where I look at this data right here. Okay, I'm wanting to look at this information here. How many times did I roll a 4? So we have the probability of rolling a 4, and that's going to be 5 out of 50. Remember, we have to simplify the fraction, so that's going to be 1/10, which is 0.1, which is 10%. So there's the probability. I didn't leave myself much room to write my compare statement because we have to write compare. Compare this to the theoretical. Well, when I look at this, I would say it is lower than expected. The experimental probability is lower than it's expected because it's theoretical is supposed to be 16.6%. Okay, now we're going to practice using this information to predict. When I usually think I'm going to predict, you're going to write a proportion. Okay, because you're setting up 2 ratios. Probability can be written as a fraction or ratio. So that's what we're going to do. We're going to be setting up 2 ratios, putting them equal to each other, and solve for what we're missing. All right, so for number 11, the table below shows the result of tossing a coin 100 times. That's the total. Results, frequency. Okay, so theoretical. How many heads would you expect to occur in 300 tosses? I'm using theoretical. So the theoretical probability for landing on a heads is 1 out of 2. I want to know how many times that's going to happen out of 300. Because remember, it's the probability is what you want over the total. So that's what we set up, the way we set up our proportion. What you want, I can't write, obviously, over the total. And now I solve my proportion. I'm going to do 2 times 150, which means that x equals 150 times. Okay. Next, based on the experiment. So now I'm looking at it from the experiment, not theoretical. I'm using this data. How many heads would you expect to occur in 300 tosses? So I have to use this information, and I'm doing the heads. So therefore, it's going to be 58 over 100 equals x over 300. Now these numbers are nice, easy, and I could just multiply like I did here times 150, but I want to review solving a proportion. So we multiply diagonally, and I end up with 100x equals, remember we do get to use a handy dandy calculator. So I'm doing 300 times 58. I can type it in the calculator correctly, 300 times 58. So we have 100x equals 17400. Divide by 100 on both sides. Notice that the zeros cancel, and we're left with x equals 174 times. Remember, if you have any questions, you can pause it and rewind, or you can come ask me. Hope you have a great day. Remember to finish the notes and the classwork homework. Bye.